Okay, so that is what is explained here. You have in the V dash GS is the input voltage, and CGST and CGT are total capacitances present between the gate and source and the gate and drain. And the resistance between the source and channel is given by RS. The resistance between the source and drain is given by RD. You have those two things in the circuit. You have RS and RD, and output side you have RDS and CDS. RDS is the drain source resistance, and CDS is the capacitance between the drain and the source. And if you want to apply low frequency to this, you will exclude all the capacitance. So if you want to apply low frequency to this low frequency approximation to this circuit, what all will go? This capacitance will go, this capacitance will go, this capacitance will go. So input side will be open. At the output side, you will have current source, RDS, RD, and RS. That is what you will have. And this is, I am considering RD and RS to be very, very high. So I am neglecting them also. So you have only one resistance, RDS. So you have this current source GM into VGS, and you have one resistance RDS. So I see here I am neglecting the effect of RS and RD, because drain current only depends on the gate source voltage VGS. So ID, this is ID, right? So the drain current depends on GM into VGS. ID equal to GM into VGS. So ID depends on VGS, the input gate source voltage. This is a simplified model of your MOSFET. So from this, I can write if I include my source resistance, then how did we have for Jfit? The same thing. So when you include RS, the circuit will be slightly different. So same way here also, I am finding the relation between VGS and VG-S, which is same. So you can see these three equations are going to be completely same as the Jfit. So the total voltage VGS will be equal to this voltage plus this voltage. Voltage across resistor, you know, it is equal to resistance into current. So GM into V dash GS into RS. So I am simplifying, taking V dash GS as common, I get VGS equal to 1 plus GM RS into V dash GS. If you put RS equal to 0, you will see that VGS and V dash GS will be same. So now I can write the expression for drain current. So ID equal to GM by 1 plus GM RS into VGS. You know, GM by 1 plus GM into RS is GM dash. So GM dash into VGS. Okay, so when you are going to consider the source resistance RS, so you have to ensure that the corresponding, you have to use the notation having dash. So whenever you are going to consider RS, you will be using G dash. Whenever you don't consider RS, you will be using only G. So remember that notation, the same notation what we assumed for Jfit, the same thing is applicable for MOSFET also. The same way how we have in Jfit 2 frequency limitation, same way here also we have 2 frequency limitation. One is called as channel transit time, and next one is called as capacitance charging time. Okay, channel charging time and capacitance, channel transit time and capacitance charging time. So channel transit time, as we have seen, it is the maximum frequency at which the device can operate. So the time is channel transit time is going to be distance by velocity. So tau t equal to capital L by Vs. So capital L is the length of your channel and Vs is saturation velocity. So when you consider saturation velocity to be 10 power 7 centimeters per second, and the length is 1 micrometers, you get the channel transit time as 10 picoseconds, which corresponds to the frequency of 100 gigahertz. So maximum frequency at which your device can operate is 100 gigahertz. If you operate beyond that frequency, then the performance of the device is not guaranteed. So please understand that. And this frequency is very much larger than your, this frequency is much larger than the frequency response of MOSFET. For high frequency analysis, you will be, whenever we are going to go for high frequency analysis, all the capacitance will come into picture. So that charging time becomes a big performance issue for MOSFET. That is going to be the second thing, which is called as capacitance charging time. So this is going to be the equivalent circuit, when you are going to consider the capacitances, you will be having CGST, you will be having CGDT, which is the total capacitance between gate and source, gate and drain. You have the current source trans conductance representing the relation between ID and VGS, and you have a load resistor across which you measure the V naught. So output voltage, you measure it across the RL, which you connect it externally. So across RL, you measure the output voltage. So RL is not a part of your equivalent circuit. You connect the load resistance externally to measure the output voltage. Okay. So this completes your unit 3. So we have completed unit 3. So today we have exclusively seen about the equivalent circuit of MOSFET and Jfet. So we have seen what is the low frequency equivalent circuit. First, we have seen what is the general equivalent circuit, and from that, by making low frequency assumptions, we have derived the approximate equivalent circuit for your small signal equivalent circuit for your JFET and MOSFET. And in both the cases, we have two conditions: without RS and with RS. Without RS means I'll be using the usual voltage VGS. With RS means I'll be using the voltage V dash GS. When dash comes, it means I'm going to include the effect of the source resistance RS in my equivalent circuit. And this both the drawing the equivalent circuit for JFET and MOSFET is going to be, the logic is going to be exactly same. The relation between VGS and V dash GS is going to be exactly same. IDS and V dash GS is going to be exactly same. And the two problems which JFET faces, same problem your MOSFET is also going to face. So when the small signal equivalent circuit, there are more similarities between JFET and MOSFET. So if you read the basic thing, the understanding is going to be same. Only thing, in the equivalent circuit is somewhat simplified for MOSFET when you compare to JFET. In JFET, you had lot of resistance and capacitance, but in MOSFET, those are all completely ignored because of the construction of your MOSFET. Okay, so